Welcome to the next lecture of linear algebra. In the previous lecture, we have discussed verification of solution of first order differential equations or differential equations. In today's lecture, we are going to discuss types of solutions of differential equations. So the first is trivial solution, a solution of a differential equation that is identically zero on any interval is said to be a trivial solution. Otherwise, it is called non-trivial solution. You can see these two differential equations here. The first one is x dy by dx plus sine x into y, and the other one is this one. We can see that y is equal to 0. If we insert y is equal to 0 here in this differential equation and here in this differential equation, both sides becomes 0. So becomes 0. This is 0 is equal to 0. So this differential equation basically it turns into an identity which is 0 is equal to 0. Similarly, if we insert y is equal to 0 here in this differential equation, then this equation also gives us identity which is 0 is equal to 0. So what is this? Trivial solution is always y is equal to 0 solution. I hope you got it. Next is the explicit solution of a differential equation. A solution which can be expressed in the form of a explicit function. I hope you know what is explicit function. Explicit function is basically we can write this solution in terms of y is equal to function of x only. So this kind of solution is called explicit solution. Again, if we insert the solution, for example, this is the solution of this differential equation, and this solution is an explicit function of x. You can see here that there is no y here. So y can be expressed in the form of x or as a function of x. Similarly, for this differential equation, you can see the solution is explicit function of x only. So this is called explicit solution. I hope you got it. Now, implicit solution, sorry. Any solution of the differential equation which cannot be expressed in the form of a explicit solution, explicit functions, then it is called implicit solution. For example, this relation is an implicit solution of this given differential equation. We can verify in two ways that whether this is a solution of a differential equation or not. How? We can take the derivative of this function differentiating implicitly. I hope you know what is implicit differentiation. We take the derivative of this function x square plus y square is equal to c. We must have c here. It's a typo mistake. So if we differentiate this function with respect to x implicitly, what do we get? 2x plus 2y into dy by dx. Now, if we solve for dy by dx, what we obtain here, it is dy by dx is equal to minus x by y, which is the given differential equation. So this function satisfies this differential equation. So it is an implicit solution. I hope you got it. If you have any question, you can ask me in the chat window or you can ask me directly. So another example of implicit solution is that if we are given a differential equation of this kind, dy by dx is equal to x square over 1 minus y square, we can take this denominator on the left hand side here and dx on the right hand side. So we can separate the variables here. We can write this given differential equation in this form, which is 1 minus y square into dy is equal to x square into, I must have dx here. It's a typo mistake. So we can separate the variables. Here we have only the y variable, and here on the right hand side we only have x variable. Now if we integrate it with respect to left hand side with respect to y and right hand side with respect to x, after integration we can have this integral of 1 is y, one is y and y square is y cubed by 3. And similarly, right hand side x square, integral of x square is x cubed by 3 plus c. So this is another, sorry, this is the solution of the given differential equation, this one. And we cannot express this solution in the form of, as a function of x. So this is an implicit solution. So it doesn't exactly look easy to write in the form of fx I have written. So this solution cannot be written in the form of an explicit function. So it is an implicit solution. If you have any question, you can ask me. Otherwise, we are going to move forward. Next, families of solution. Families of solution. You can see on the previous slides here, particularly not this one, this one. While if we solve a differential equation of first order, we basically try to find y as a function of x. And while integrating, we must have an integration constant in the solution. As we have first order differential equation, so in order to solve it, we integrate it only one time. So when we integrate it only one time, we must get a constant, which is a constant of integration. So solving a first order differential equation involves one constant of integration. So where this constant of integration is an arbitrary constant. So this solution contains one constant. If we change the value of a constant, the function will change. So if this is arbitrary constant, the C belongs to R. How many values can C can take in R? C can take infinite many values. So how many solutions do we have? Infinite many solutions here, unless we find some particular value of C. So set of all these solutions, they form a family of solution. We call it family of solution because C is arbitrary constant. Sorry. Because C is arbitrary constant, it can take any value in R. So how many values it can take? It can take infinite many values. So this is basically, this forms an infinite many solutions. How many constants it involves? One constant. So turn off your mics kindly. So how many solutions do we have here? Infinite many solutions. And the set of all solutions is called a one parameter family of solution. So this is what we are going to discuss here in the families of solution. So I have written here, solving a first order differential equation, we usually obtain a solution containing a single arbitrary constant. So I have explained you all this. So a solution which contains an arbitrary constant C, we can represent that solution in this form. G of x, y, c, because the solution is function of x and y, and there is one constant, and the set of all solutions, this one, which contains only one parameter, is called a one parameter family of solution, or we call it general solution. For example, in example 3, the solution in example 2 on the previous slide, this one which I explained you earlier, this can be written in this form, and further we can say that this is a solution which can be written in this form, g of x, y, c. So this solution contains one constant, so it is called one parameter family of solutions of the first order ODE. Or we can call this one is as a general solution of the given differential equation. I hope you got it. If you have any question, you can ask me. Similarly, we can have two parameter family of solutions, three parameter family of solutions, and in general, n parameter family of solutions. So two parameter family of solutions, how can we obtain it? If we solve a second order ODE, ordinary differential equation, it will involve two constant of integration. There is a question in the chat window. Can you repeat the last slide? So let us go on the previous slide. This one, we were discussing family of solutions. I told you earlier that if we have a first order differential equation, in order to solve it, means in order to find this solution y, what we do, we integrate it only one time. If we integrate it only one time, we must have one constant of integration. If we have one constant of integration and this constant is arbitrary, so c can take any value in the real numbers. So how many constants? This solution involves only one constant. So how many solutions are there for different values of c? We have infinite many solutions. So this set of solutions is called one parameter family of solution because we have only one parameter in this solution. I hope that you got it. So similarly, we can have two parameter family of solution if we try to solve a second order differential equation. Second order differential equation involves two derivatives. So in order to reverse these two derivatives, what we have to do, we have to do integrations two times in order to reverse these two derivatives. So if we do integration two times, we must have two integration constants. For example, C1 and C2. So in order to get the solution of a second order differential equation, we must integrate it two times so that we get two integration constants C1 and C2. So the solution must contain two arbitrary constants, C1 and C2 here. This one. This is the general solution, or we call it two parameter family of solutions or of that given differential equation. Similarly, if we generalize this concept, if we have an nth order ordinary differential equation, we have to integrate it n times, and we will definitely get n constants of integration. And the general solution can be written in this form, and this is called n parameter family of solutions or the general solution. I hope you got it. And these are infinite many solutions for different values of c. All these constants of integration, they belongs to R. They are real numbers. So we have infinite many solutions. That's why we call it family of solutions. I hope everything is okay with you. If you have any question, you can ask me. Now, what is the particular solution of a differential equation? A solution of a differential equation which is free of arbitrary constants means there are in every solution in the previous slides we discussed that if we have first order differential equation, it must have one constant of integration when we integrate it. But there are other solutions, or we can take particular values of these constants as well. If a solution of a differential equation does not involve any arbitrary parameters or constant of integrations, it is called a particular solution. Particular solutions can be obtained from the general solution by assigning specific values to the arbitrary constant. For example, if we have this one parameter family of solution of this differential equation by choosing particular values to this C. Here, if we choose C is equal to 0, or we can choose C is equal to 5, we obtain these two solutions. So these are particular solutions. Particular solutions or specific solution which can be obtained from the general solution by assigning or by taking different values of C. So this is called a particular solution. Particular solutions are normally we can obtain particular solution of a differential equation if we are given some additional condition along with that differential equation. So we'll discuss this later on, how to find particular solutions and how to find the value of some particular or some specific values of the constant of integration C involving in the general solution or one parameter family of solution. So we'll discuss this later. For now, particular solution is a solution which doesn't involve any arbitrary constant. This is called a particular solution. Now we are going to, for example, in this figure, you can see in this figure there are infinite many solutions. And what are these particular solutions? They are only this one where y is equal to x square, and this one is where y is equal to x plus 5 whole square. So you can see a particular solution between these curves. So next is initial value problem. Initial value problems are basically the problems in which we are given differential equations along with some condition. This condition can be on the initial value of the differential equation. For example, if x is defined on this interval a, b, then this differential equation is defined along with some initial condition. Initial condition means we know the value of this y at the starting point of the domain, y at a. This is an additional condition which is given along with the differential equation. For example, in physics, if a car is moving, then we can find its displacement, velocity, or this differential equation, this kind of differential equation can express the velocity of a moving car, or if we throw a ball, it can represent a velocity of the ball. Along with this condition, the car has started its journey from x is equal to a. Now we know that its displacement or its velocity at the initial point, it has what? So we can place an additional condition like this on the differential equation. If we have first order differential equation, we have one constant of integration. So we define only one condition along with the differential equation. This condition helps us to find the constant of integration, which involves in the first order differential equation. Now, if we have second order differential equation, we must have two constant of integration. So in order to find the values of those two constant of integration, we define two conditions along with the given differential equation. So if this is the differential equation, then d square y by dx square can be, this differential equation can express the acceleration of a moving body. So in order to get the specific or particular solution, we must have two conditions because there are two derivatives involved in this differential equation. Yes, let me, who is in the waiting list? Let me, just a second, let me add him. Yes, 50. So I admitted them all. So now we must have two conditions. because there are two constant of integrations in the second order differential equation. These two conditions, the first condition is on y and the second condition is on y dash, first derivative of y. So these two conditions will help us to find two constants of integration in the solution of this second order differential equation. This is how we can define, and these kind of problems, this first one is called initial value problem, because there is an additional condition on the initial value of the domain. That's why we call it initial condition. And this is again an initial value problem along with two initial conditions. These are also initial conditions because they are defined on the initial value of the domain. And this is the velocity condition or the y derivative condition defined on the initial value of the domain. So that's why we call them initial conditions. If you have any question, you can ask me. Similarly, we can generalize these initial value problems. We can have third order initial value problem. We can have fourth order initial value problem. Third order initial value problem, definitely we must have three initial conditions in order to find three constant of integration. And if we have nth order differential equation, we must have n initial conditions in order to find n constants of integration. I hope you got it. If you have any question, you can ask. There is a question in the chat window. So don't we have both x and y to find the values of the parameter? Yes, we have both. This is basically the value of x. This is value of x at the starting point, and this is the value of y at the starting point. If we have these two values, we'll do examples for these problems later on. You would definitely understand. If you have any further question, you can ask. So now, example. This is what you were talking about. Here is an example of initial value problem, first order initial value problem. We have this is a differential equation, y dash whole scale is equal to 4y, and this is the initial condition which is given along with the given differential equation in order to find the constant c, constant of integration. Y of 0 is equal to 16. Now we know that on the previous slides we know that this is the solution of the given differential equation, this one, because it satisfies this. So if we use this initial condition, how can we use it? Y of 0 is equal to 16 means we insert the x is equal to 0, x is equal to 0 here, and y is equal to 16. We have values of x and y both. If we insert x equal to 0 here and y is equal to 16 here, we can get c is equal to what? C is equal to 4. So now this is our required particular solution and corresponding to this one. This is particular solution because we have obtained this solution from the general solution by assigning some or by finding some specific value of c. So this is particular solution. And this is how we can find the value of c, by using this given additional initial condition along with the differential equation. I hope you got it. If you have any question, you can ask. Yes, there is a question in the chat window. Which one? What we have, -4. Yes, you can have -4, but in that case you can have two solutions. But you can interpret two solutions, and then you choose that solution which basically satisfy all the other conditions of the differential equation. For example, the x must be between 0 and 1, and this condition must also be satisfied here. You can have the other solution as well. Okay. I hope that answers the question. If you have any further question, you can ask me. So this one. So in general, I have told you general initial nth order initial value problem is basically what it involves nth order differential equation. This one, its order is n, and we must have n initial conditions in order to find all the arbitrary constants involved in the general solution or n parameter family of solutions. We have already discussed it. Let's move forward now. Applications, we are going to discuss applications in the basically in the next topic, which is when we'll discuss only the first order differential equations. Let's now stop it here, this one, and we are going to discuss now only the first order differential equations. Till now, if you have any question, you go ahead, you can ask me. Otherwise, I'm going to open the new slides which contains only the first order differential equations. Now we are going to discuss this, how to solve these differential equations. In the previous lecture and in this part of lecture, we discussed what are differential equations, what is their order, degree, what are the solutions, type of solutions, what are initial value problems. Still, we haven't discussed how to solve these differential equations. Now we are going to discuss how to solve these differential equations. Now we are going to discuss only the first order differential equations. The first order differential equations are the, I hope you know it, what is the first order differential equation. We have discussed first order differential equation in the previous lecture. There are different forms of first order differential equations. For example, this one, we can write first order differential equation in this way: dy by dx is equal to f of xy. We can write in this way, which is the general linear first order differential equation. We can write the first order differential equation in this way, which is the standard form of linear first order ODE. We can write the differential equation in this form, where m of xy is a function of xy times dx, n of xy dy. We can simplify it and we can obtain similar kind of notation which we have here. We take this thing on the other side, and then we divide with the n of xy, we get a differential equation of this form. So here what we have separated dy and dx differentials. So another form is this, which is basically the initial value problem of the first order. These are all different types of differential equations we can have. Now, is there any physical significance of these first order differential equations, or are there any applications of these first order differential equations? I told you how we can derive these differential equations mathematically in the start of the previous lecture. Now we are going to discuss how physically we can obtain first order differential equations. For example, this one, the first application is Newton's law of cooling. What is this? Newton's law of cooling states that if we have any hot object, for example, a cup of tea. The cup of tea is basically its temperature is very high as compared to the room temperature. So how does that temperature of the cup of tea decreases with the passage of time? So we can this can be described with the help of Newton's law of cooling. The rate at which the temperature of body, for example, the coffee cup, changes is proportional to the difference between the temperature of the coffee cup and the temperature of the surrounding, means temperature of the room. And that is called the ambient temperature or the surrounding temperature. If you have a hot cup of tea, how does its temperature decrease? This is what Newton's law of cooling tells us. So the rate of change of the temperature of some body, which is definitely hotter than the temperature of the surrounding, is proportional to the difference. This is important. Difference between the temperature of a body and the temperature of the surrounding medium, which is called ambient temperature. So if we represent T of T is the temperature of the coffee cup, and Tm is the surrounding temperature, and the temperature is definitely the function of time, then how can we express the rate of change dt by dt? It is proportional to difference between the temperature of the coffee cup and the temperature of the surrounding, which is ambient temperature. If these two are proportional, then we can write them in this form by writing a constant of proportionality here. It's a mistake here, typo mistake. I should have written a constant k here, which is the constant of proportionality. Along with, we must know, we can know, or we can calculate the initial temperature of the coffee cup, and that is our initial condition. I hope you got it. Now, what is this? This is a first order initial value problem. This thing. Along with the initial condition, we can use this initial condition to find the integration constant. This is how we obtain a first order differential equation or first order initial value problem. If you guys have any question, you can ask. Another application of the first order differential equation is this thing, spread of a disease. I hope you can use these kind of models in order to calculate how much corona cases will be there after some time in Pakistan or in the world. So these kind of models can be used in order to compute the possible or expected spread of disease. Now, what is this model? There is a question in the chat window. So these kind of questions you can ask me after the lecture, because you can ask questions related to the lecture during the lecture. Other questions you can ask after the lecture. Now the question is, a constant k would mean it is a linear proportionality, but COVID would be exponential. Yes, this is basically a primary, or you can say an elementary prototype model. We can add many other factors in the model in order to get different factors. So this is basically the primary or basic model where we start. So COVID-19 can be, you can compute the expectations after some time by using similar kind of models. So this is basically the very basic model, which doesn't include many assumptions. If there are some other assumptions, we can add in this model in order to basically project the number of cases of COVID-19 in the next month, or maybe after a couple of months. So what is this model? A contagious disease, say a flu virus, for example, COVID-19 in these days, or maybe Ebola, maybe other viruses, is spread throughout a community by people into contact with other people. This is how the contagious disease spreads among the community. So what we do here, we assume that let x of t denote the number of people who have contracted the disease, and y of t denote the number of people who have not yet been exposed to that disease. Now, the rate dx by dt, because what we are going to find, we are going to find the number of people which will contract the disease after some time. So what we have expressed here, x of t, it is basically the number of people who have contracted the disease. So we want to calculate expected number of people who will contract the disease after some time. And y is the number of people who are not yet being exposed to that disease. Now, how this disease spreads? When the people X and the people Y, they interact with each other. This is how a contagious disease spreads. So now you can say that the rate dx by dt at which this disease spreads is proportional to the number of interactions. Number of interactions between these two groups of people. Means you can say if X is the number of people who have already contracted the disease and Y is the number of people who are not yet been exposed, then their interactions could be the product XY. Now, dx by dt, we can say that dx by dt is proportional to the number of interactions between X and Y. If this is proportional, then we can write this thing in this form by writing a constant of proportionality. Yes, there's a question in the chat window. It is further assumed that the number of interactions between X and Y is their product, XY. It is also assumed here, and we can assume it. I have explained it here at the bottom of this slide. Further assume that the small community have fixed population of n people. For example, there are no cases in Lahore and we have n number of people. If one infected person is introduced into this community, means we leave one infected person in Lahore, then what would be the total population then, total number of people in Lahore? It is x plus y, which is n plus 1. Now, from this relation, we can find the value of y, because here what we are going to find here, we are going to find x. So what is y? We should not have another variable y in the model. So by assuming this thing, we can find the value of y from here, and by inserting value of y here, we can obtain this model, which is dx by dt. There is a question in the chat window. They are jointly proportional. What does jointly proportional means? Jointly proportional means the rate of change is proportional to both. Or you can say, we assume here that the proportional to their product, the number of interactions. Okay. So now this model has been obtained, dx by dt is equal to x time. Here we inserted the value of y with the initial condition, how many people we introduced in that small population. For example, Lahore, only one person have been introduced which was infected. So that's why initial condition could be at time 0, only one person was introduced in Lahore. There's another question in the chat window. No? Okay. I hope you got it. If you have any further questions, you can ask me. Now, these are a couple of physical applications of first order differential equations. There are many you can find in the book of Howard and Tandon. I think a couple of books I have uploaded on your LMS. You can find many applications of first order differential equation. Similarly, there are many applications of second order and third order differential equations. Why the condition x, there is a question, why the condition x is equal to 0? Why is it so? Why we put this condition along with this differential equation? I have explained you earlier that we have assumed here a small community has a fixed population of n people. What we do here, we introduce one infected person in that community. For example, there were no cases of COVID-19 in Lahore at certain time. One person came in who was infected, and the infection or the number of infected people basically start increasing by introducing only one infected person. Okay, at time 0, we introduce how many infected person? Only one person. That's why we can put an initial condition, this one along with this differential equation, which help us to find the constant of integration. I hope that answers the question. There's a question in the chat window. If it is jointly proportional, should we have two different constant of proportionality? Yes, you can have two, but the product of two constant is a constant. So ultimately we get only one constant. I hope that answers the question. Now, the first kind of differential equation which we are going to discuss, how to solve these first order differential equations. The first kind of differential equation is basically the separable first order differential equation. Now we are going to discuss how to solve these first order initial value problems or first order differential equation. So I told you any differential equation basically in the start, that any differential equation can be written in this form. In this form, dy by dx equal to f of xy. Now, if this function f of xy, it is the product of two functions, independent functions of x and y. So we can say that that differential equation is a separable differential equation. In separable differential equation, usually the differential equation have this form, in which we can see that we have two functions which are independent functions of x and y, and they are basically multiplied with each other. So this kind of differential equation in which we have two independent functions of x and y being multiplied, we can separate the variables in this kind of differential equation. How can we separate? We take this differential dx on this side and this function of y on the other side here. So what we obtained here by separating the variables, we have separated the variables. You can see there here on the left hand side we have only y variable, on the right hand side we have only x variable. So now we integrate both sides with respect to, here on the left hand side with respect to y, and on the right hand side with respect to x. So by integrating both sides and then integrating, what we get this. We assume that the integral of 1 over h of y is what? It is capital H of y, and the integral of g of x is capital G of x. We assume that these are the integrals of these two integrals, plus a constant of integration. When we integrate some function, we must have a constant of integration. We can have two constant of integration, one on the left hand side and one on the right hand side. But we can take this constant on the right hand side, and then the subtraction is another constant. We call that constant a C constant. So we can write here one constant of integration only on the right hand side and not on the left hand side. So it is basically the same. I hope you got it. Separable differential equations. If you have any question, you can ask me. Otherwise, we are going to discuss examples of separable differential equations. On the next slide, I have provided a couple of examples. Number one is this one. Now, you can see that in this differential equation, we cannot separate the variables. Can we separate the variables here? No. So this is not a separable differential equation. Whereas in this differential equation, we have two functions. One is x of y and the other is function of y. These are separate functions of x and y which are being multiplied. We can separate these two functions. we take this y square on the left hand side here, and we take this d of x on here on the right hand side. So we have separated the variables. Once we have separated the variables, we take the integrals on both sides. You can see that now we have integral of 1 over y square dy, integral of x e raised power 3x. Now, integrating both sides, I hope you know how to integrate these kind of simple functions. You can integrate them and you can obtain the solution along with the constant of integration here. Now, we try to express this function as an explicit function of x. If we can express this solution in terms of explicit function, then we'll obtain explicit solution of the given differential equation. Otherwise, we can stop here and we can say that this is the solution of a differential equation. It could be explicit, it could be implicit. So there is a question in the chat window: separate functions will always be product of two variables, separable functions. There might be, we can separate them, but you have to investigate whether these two functions are separable or not, because there could be different forms of the functions which, by looking very closely, you would judge that we can separate these functions. Because this is a very simple separable. I have given two separate functions, but there are some kind of complex differential equations in which separating functions is not that evident, obvious. So you have to basically closely look at the differential equation, and you have to separate the functions. Okay, it is not always obvious. You have to look into it. I hope that answers the question. Now, next, another example is this one. Now, I have given an example of initial value problem along with the initial condition. For this initial value problem, we will also try to find the constant of integration. Now, this is the differential equation. We can easily separate the variables. We have x, y power 1 by 2. We can take y power 1 by 2 on the left hand side and dx on the right hand side. We have separated the variables. Now, integrating on both sides and adding a constant of integration, we can obtain this solution very easily. Now, here we have c by 2. Yes, c by 2 is another constant. If c is a constant, we can say it c1, because we simplify our solutions as much as possible. If we have some constant multiplied with the some real number multiplied or divided with a constant, we can say this is another constant c1 in order to simplify the solution. Now, using this initial condition, what we do, we insert the value of x is equal to 0, x equal to 0, and y is equal to 0. So by inserting y0 and x0 here, you can see that c is what? C is 0. If c is 0, then our solution is this thing. It doesn't change anything if we do not reduce this c by 2 into c1. Does it change anything? It doesn't change. It will remain. Even if we write c by 2 and we insert x equal to 0 and y is equal to 0, c by 2 will be 0 and ultimately c will be 0. It doesn't change anything if we try to simplify c by 2 into c1. So don't worry. If you don't understand, if you have any confusion, you can leave it c by 2 as it is. I hope you understand everything. If you have any question, you can ask me. Otherwise, we are going to the next slide. And on this slide, I have given you a relatively complex example. If we look at this differential equation, by the first look, you won't understand whether we can separate the variables or not. You can't judge. So in fact, by looking closely at this differential equation, it is a first order differential equation, and we can separate the functions because we have a function of y here, function of x here, function of y here, function of x here. So we can separate these variables. It is a separable differential equation. What we do here, we keep this dy by dx on dy on the left hand side, and we take this term on the right hand side here, dx here. Now what we do, we divide e raised power y on the left hand side here, and we divide this cos of x on the right hand side here. Now you can see that the variables have been separated. The variables have been separated. Now we can integrate on both sides. By integrating on both sides, e raised power y, integral of e raised power y is e raised power y, and y e raised power minus y, we have to apply integration by parts here, which I have shown here, and integral of sine x is cos x. So after integration by parts here, we can obtain this solution along with this constant of integration. Now this is our solution. We cannot separate x and y further. We cannot obtain explicit solution or the explicit function. So we leave it here. This is our solution. This is our general solution. This is our one parameter family of solution. Now we can use the given initial condition and we can find the value of c. Now by inserting x equal to 0 and y is equal to 0 here, e raised power 0 is 1. We have 0 here, so it becomes 0. E raised power 0 is 1. So we obtain here, and cos of 0 is 1. We get minus 2 here. So c is what? We obtain the value of c is equal to 4. By inserting this value of c back into this solution, which is the general solution, we obtain a particular solution of the given differential equation. If you have any question, you can ask me. I hope you understand everything. Now we are going to the next slide. You don't have any question? Okay. These are some of the exercises which I have included here in the slides. You can try solving these equations. These are all separable differential equations. I request you to solve these equations so that you can have practice how to solve separable first order differential equations. So that's it for separable differential equation. Now we are going to discuss linear first order differential equations and how to solve them. Now in the start of the lecture, I have told you, I have shown you different forms of first order differential equation. I told you this is what? This is the general first order linear differential equation of first order. Yes, this is the general form and this is the standard form. We can always convert the general form into standard form by dividing whole equation with this coefficient a1 of x. We can obtain or we can transform this general first order linear differential equation into this form. I have explained you earlier how. Now, how to solve this differential equation? We are going to discuss the solution of this differential equation, not this one. If we are given this differential equation, we can convert it into this standard form. So first we have to convert the given differential equation into standard form and then we start solving it. I hope you got it. How do we solve this differential equation? We calculate integrating factor of the given differential equation in this one. How do we calculate the integrating factor? We see what is this function p of x along with the sign here. This is your function which can be computed from the given differential equation, which can be written or which we can see from the given differential equation, this p of x, along with the sign. The integrating factor is e raised power integral of p of x dx. This is how we compute the integrating factor. Why do we compute this integrating factor? Because when we multiply the given differential equation, this one, with the integrating factor on both sides, you can see here, we multiplied this integrating factor on both sides of this differential equation. What we obtained, integrating factor into first term, integrating factor into the second term, and integrating factor on the right hand side. There's a question in the chat window, sir, what if there are more functions with p of x on the left hand side of the equation? There should not be more functions, because if we are given this kind of equation, we can always convert this differential equation into this form by dividing this coefficient function throughout this differential equation. Then a naught over a1 is basically our p of x. Okay, there must be one more thing which is important. This solution procedure is only valid for this kind of differential equation, not for any other kind of differential equation. Similar as we discussed separable differential equation, that procedure is only valid for the equations in which we can separate the variables. Now, what is the purpose of integrating factor? This is what we are discussing here. We find the integrating factor and we multiply this integrating factor on both sides of this equation, on this side and on this side and on this side. There is a question, p of x should not calculated at this, then why? P of x can be calculated in this way. P of x could be a naught over a1 of x. So the simple thing is, if we are given this kind of differential equation, which we can see that it is a linear first order differential equation, in order to solve this kind of differential equation, first what we do, we write that differential equation in this form, in the standard form. Okay, what is the benefit? This is what we are going to discuss. Once we have equation in the standard form, we can find the integrating factor in this way, and then by multiplying that equation in the standard form with this integrating factor on both sides, you can see that this left hand side has become the combined derivative of integrating factor and y. Now this left hand side has been converted into this form. You can verify it. If you take the derivative of the product of these two functions, what we do, how do we use the product derivative of product of two functions? First function as it derivative of second function, this one. Now in the second case, plus derivative of this thing is what? It is e raised power integral of p of x dx times the derivative of this thing. What is the derivative of integral of p x dx? Derivative and integral has been cancelled and we only get p of x times second function remains same here. So this left hand side has become the derivative of product of this integrating factor and the y, this one. You can verify it. Right hand side remains the same. Now on the left hand side we have derivative of this function. Now this expression can be integrated with respect to x on both sides. Kindly mute your mic. Someone has unmuted his mic, so there's a noise coming out here. So thank you very much. So I hope you understand this point. what is the purpose of integrating factor? Integrating factor, when we multiply on the left hand side of this standard form of the first order linear ODE, it transforms this left hand side into the derivative of the product of this exponential, sorry, integrating factor and y. This is the purpose of integrating factor. Otherwise, we cannot solve this linear first order ODE. I hope that answers the question. If you have any further question, you can raise your hand and you can ask me question, or you can ask your question in the chat window. I repeat here, there's a question. How can you explain this again? I'll explain it further with the help of example. Now, once we obtain this kind of expression, you can see that if we integrate here with respect to x, and also here we can integrate with respect to x. Now, integrating both sides with respect to x, now this derivative and integral can be cancelled, and we obtain only this expression which is inside this derivative. Okay. Kindly mute your mic. There's a noise coming out there. Thank you very much. So now we are going to the next slide, this one. Now integrating, I have written the same thing here. Integrating, we obtained this expression on the previous slide. Integrating both sides, this thing here, the derivative and integral can be cancelled, and we obtain only this expression which is inside, and here the integral remains. Now this integral, basically we can have a constant of integration along with this integral after doing integration. And then what do we need here? We need only y here. We don't need this. What we do here, we divide this on the other side, and we can take it on, we can take it in the numerator, and we'll have negative sign here, because when we divide this on the other side, we can take it on basically in the numerator, and we definitely have to put a negative sign here. So this is how a linear first order differential equation can be solved. Now we know the Q of x, we know P of x, we can find this, we can multiply the resultant of this, this with the Q of x, and then we can integrate the resulting function with respect to x. We can obtain the solution. Similarly, we can solve this integral as well here. So this is how we can solve a general linear first order differential equation. Now let's discuss this thing with the help of example. If you have any question, you can ask. What is the procedure? I have written here the procedure of solving linear first order ODEs. What steps we follow here is put a linear equation in the standard form if it is not already in standard form. Okay, this is the first step. What is the second step? You find the integrating factor, you identify the P of x in the standard form of the given differential equation. When you identify P of x, then you can find the integrating factor, this thing. Now, what we do in the step 3, we multiply the given equation with this integrating factor, and the given integration will be converted into integrating factor times y is equal to integrating factor times the right hand side. Now, what is the last step? You integrate both sides with respect to x, and after solving it, you can have the solution. There is a question in the chat window, sir, what if we swap the places of Q of x and P of x? Would it change anything? Yes, definitely. Then in the integrating factor, you must write here Q of x, because P of x should be the coefficient of what? P of x should be the coefficient of y. You can see that here P of x should be the coefficient of y, and Q of x, it is a single function of x. It doesn't involve y. Another question, why we are using exponential? In order to get this left hand side, and this will be converted into the derivative of product of two functions. If we do not take here exponential, this left hand side cannot be converted into the derivative of product of two functions. You can try it. Okay. There is a question here, why dot p of x is linear? Yes, because we see the equation linear in y only, not in x. So this is linear because y is linear here, the degree of y is 1 here, the degree of y is 1 here. That is why we call it linear. The standard expression for the integrating factor will remain same. The formula for integrating factor is this. It is what? E raised power integral of p of x dx, where p of x will change for different equations. P of x, this formula will remain same for every first order linear differential equation which is written in this standard form. P of x will change, the formula will remain same. I hope that answers the question. Now, with the help of example, this thing, let's discuss this example. I have chosen a very simple example in the start. Now, what is this example? We have to solve this differential equation, which is a linear first order differential equation, which is already given in the standard form. Now, what is P of x? P of x is 3. We cannot take this as a P of x. This is the right hand side. Okay, the P of x is always the coefficient of y. It is plus 3. If we have a negative 3 here, then P of x must be negative 3. So we have to take the sign of P of x as it here. Okay. Now, what is the integrating factor? It is e raised power integral 3 dx. Now, what is the integral of 3? It is 3x. Now, this is your integrating factor. We multiply the given equation with this integrating factor here on both sides. What do we obtain here? E raised power 3x, e raised power 3x, and e raised power 3x on the right hand side. Now you can observe that this left hand side has become the derivative of what? Product of e raised power 3x and 3x. If you simplify this derivative, you must get again this left hand side. I hope you can try that. What is the derivative of, e raised power 3x remains same here. We take the derivative of y. So it is what? dy by dx. Now, what is the derivative of e raised power 3x? It is e raised power 3x times 3 into y as it. So what we obtain here? Exactly the left hand side in this step. Now, I hope you can see what is the importance of integrating factor and how can we compute it in this way and why we have computed this in this way. Because the integrating factor, when we multiply it on the left hand side of the given differential equation, it transforms, it converts the left hand side into the derivative of product of integrating factor and the dependent variable y. The right hand side remains same. Now what we do, we integrate this thing on both sides by integrating here with respect to x dx. You can see that the derivative and integral can be cancelled and we obtain only e raised by 3x into y and the integral of this thing with respect to x. There is a typo mistake here. I should have written here d by dx. This one. Now we obtain this one. Now after integrating this term, what do we obtain here? The integral of e raised by 3x is e raised by 3x divided by 3. So 3 2s are 6 here. We can cancel them. And what we obtain here, e raised by 3x plus c. Now this term can be divided on the other side here. Now when we divide this thing here, e raised by 3x, e raised by 3x has been cancelled, and e raised by 3x multiplied with this thing. Because when we divide it here, we can take it in the numerator and we get e raised by minus 3x into 2 times e raised by 3x plus c. When we multiply this thing inside here, e raised by minus 3x into e raised by plus 3x, it will be cancelled, and we get 2 plus c times e raised by minus 3x. This is our required solution. And this solution, you can see, is valid for all values of real number. We have to find the intervals also where the solution is valid. So you can see that this function is defined for all values of r. So this solution is valid for all values of x in r. So there is a question in the chat window. Can you repeat the calculation in step 3? This one. So d by dx of product of this function is what? You take the derivative. You take this function as it is. This one. You take the derivative of y is what? It is dy by dx. And now here you take the derivative of e raised by 3x, which is what? E raised by 3x times 3. I hope you know how to take the derivative of e raised by 3x. Now, there is another question. Why we are not writing e raised by 3x as c, as both will be constant. There is an x here. There is an x here. It is not a constant. E raised by 3x is a function of x. It is not a constant. So we cannot write this thing as another constant. I hope you got it. There is a question in the chat window. Why we are not writing c e raised by 3x as a constant? Because this is a function, not a constant. Agar hamare paas, if we have 2c, for example, this one, then we can write this thing another constant c1, because both are constants. But if we have a function multiplied with the constant c, then we cannot simplify it. It will remain same in the solution. I hope you got it. There's a question, the validity of the answer. Yes, this answer is valid. It is not undefined for any value of x, because exponential functions are always basically defined. They cannot become infinity. So this function is valid for all values of x. So we can say that this solution is valid for all values of x in R, or valid on R. Just give me 1 minute and then I'll finish. Now I have taken another example in the similar manner, just a couple of minutes and then I'll finish. Another example. In this example, I have taken this equation. It is not in the standard form. It is the general linear first order differential equation. What we do here, we write this general form into standard form first. How can we write it? We divide the whole equation with x. We have here now 4 by x, and x raised to the power 6 will be x raised to the power 5 into e raised to the power x. Now this equation is now in the standard form. Okay, now this is in standard form. Now what is p of x? P of x is the coefficient of y, which is what here? Minus 4 by x. Okay, now this is minus 4 by x. Integrating factor is what? E raised power integral p of x dx, which we can simplify in this way, because 4 can be taken outside. 1 over x, integral of 1 over x is log x. We can further simplify it. We can take this minus 4 on the power of power of x. Then e and log can be cancelled. I hope you know it. and what we obtain, x raised to power minus 4 is the integrating factor. Now multiplying, integrating this equation by the integrating on both sides, integrating factor on both sides, we obtain this, the derivative of product of integrating factor and y, and when we multiply this thing on the right hand side, x raised to power 5 and x raised to power minus 4, we get x only. Now integrating on both sides, we can get this thing plus a constant c, and after simplifying we get this solution. Now we can use this initial condition by inserting x equal to 1 and y is equal to 2. We can obtain the value of c, which is 2. Now the inserting this value of c back into this general solution, which is also the one parameter family of solution, we can obtain this particular solution. Now this solution is valid in this interval. Why? Because you can see that here, when we divide x here throughout on both sides of this equation, x should not be 0 here. X should not be 0, otherwise this equation will not be valid. So we must exclude this point from the domain. So we must exclude this point from the domain. Now this is our solution, but this solution along with this condition that x is not equal to 0. So this solution must be valid on union of these two intervals, which excludes 0 from R. So that's why we excluded x equal to 0 here. I hope that you understand it. If you have any question, you can ask me. Otherwise, we are going to stop here. In the next lecture, we'll discuss exact equations. There's a question in the chat window. On 0 side, I don't understand this on 0 side. Can you repeat that question? Okay, I am going to stop today's lecture here. If you have any further question, you can ask me. There's a question, sir, this is not defined on x equal to 0. Yes, it is not defined, because here you can see that we have divided this whole differential equation by x on both sides. Now here x is in the denominator. This equation is not valid on x equal to 0. If this equation is not valid on x equal to 0, then we can say that this solution is valid, but this will create problems while basically plotting the solutions, or you can say analyzing the solution of this differential equation. Okay, I hope that answers the question. So now I'm going to stop here today. If you have any question, you can ask. So maybe see you next time. I'm going to stop the